Hey everyone, welcome to InsightsByRish. In today's video, we are going to implement a project of industrial gas production forecasting using Arima, which is a time series forecasting project. Now, this will be a univariate data because Arima can only handle the univariate data and not the multivariate one. Arima basically stands for Auto-Regressive Integrated Moving Average, and we are going to make use of this model to forecast the industrial gas production. For this project, I am going to make use of this particular data set from Federal Reserve Bank. As you can see, I will provide the link of this in the description box. Do check that. So once you click on this download, it will show you various options about the CSV file, Excel data, or in which particular format you want to download the data. So I have selected the CSV one. I have downloaded this particular data in the CSV format. And after downloading that, I have imported that particular file here in the Google Colab environment. After you are done with all this stuff, let's start implementing the project. So first we will say import pandas as PD. First we will start loading the data here. Let's run that. And let me also give the headings here. The first one that we are going to do is loading the data. Fine. After loading the pandas, next we will import the data set here. So let me say df is equal to pd.readcsv, and here I will provide the path of the CSV file. Let's check the dimension of this using the shape method. So this data set consists of 1026 rows and 2 columns. Let me also display it for you. So as you can see, we have 2 columns here. One is date and another one is IGP. This is what we are going to forecast. This will be our forecasting column. So this was all about loading the data. The second procedure or the second stage here would be pre-processing the data. You have to perform a lot of pre-processing before beginning with time series forecasting. So let me say here data pre-processing. Fine. So the first thing that you want to do here is first you have to check for the null values. Let me say checking null values. So here I will say df.isene.sum. This will give us the count of null values in each column, and as you can see everywhere it is 0, which means we don't have any null values in any of the available column. After that, next we will check the data type of these columns. So for that we will say df.info. This will display us the column along with its data type. So as you can see, the column date is in object data type and the column IGP is in float data type. Now the IGP is in float data type, that's good, but the date column shouldn't be in object one. It's mandatory to convert this into date time data type. So let me say here converting the date column into date time data type. Fine. So for that, what we are going to do, we will say here df, the column name which is date in uppercase, then pd. Here we are going to make use of inbuilt method from pandas, which is to_datetime. This will help us to convert the data type of a column into datetime format. And here we will pass the date column again from the df data frame. Fine. So this is how you convert the date column into datetime. Let's run that. And let me again say here info to confirm. Fine. So as you can see, now the date column has been converted into the datetime data type. The next thing that we want to do here, while performing the time series forecasting using Arima, it's mandatory to have this date column as your index. Right now, if you see here the range index, which is for 1026 entries, it's some random integers from 0 to 1025. So these are right now our indexes. If you even see here, you can see this 0, 1, 2, 3, 4, these are your indexes, but you don't want that. You want your date column as an index. So next thing here is making the date column as index. So here let me say df.set_index. This is an inbuilt method again, which helps you to make a column as index. So here we have to pass the column name. So the column name is date, and in order to make the changes permanent, you can say here in place is equal to true. Let's run that. And let me again say info here, df.info. So now you can see it will just show you a single column here of IGP, and the date column has been transferred to the index portion, as you can see. And now we have this date time index, and for 1026 entries, now our indexes start from 1939 0101, which is year, month, day format, up till 2024. Even if you try to display that here, let me say df.head, you can see now the date column is your index, and this is what you wanted to do. So we are done with all pre-processing of data. So this was the second stage of data pre-processing, where we tried to convert the data type of date column from object to date time, and then we made it as index. The third stage here would be checking the stationarity of the data. Let's talk about that in detail. Just a minute, let me give the heading here. So checking the stationarity of data. So whenever you are working with the Arima model, it's mandatory for your data to be stationary, which means the data should oscillate around the mean of 0 and should have constant variance. If your data is not oscillating between a mean of 0, if it is having any kind of uptrend or downtrend, then basically that data is not stationary. So you can check the stationarity of the data with two methods, and let me display you both the methods. So first, to check the stationarity of the data, you will plot the data that you have. So here I will say df, which is our data frame name, dot plot. And this particular method will only work if you have the date column as your index. If you have not made the date column as your index, this method won't work. Fine. And then give the figure size whatever you want here. So let me give it as 18,5. This is purely based on trial and error. Let me run that. So as you can see, right now we are having an uptrend in our data. There is no constant variance, and also the data is not oscillating around the mean of 0. Probably there is an uptrend, and we don't want that. We want that the data should be constant throughout the time period. So this was the first way of checking whether the data was stationary or not, by plotting it. And if you find that there is an uptrend, which means the data is not stationary. The second way is more practical and mathematical. You will make use of ADF test, which is augmented Dickey-Fuller test, that will return you a value, p-value, and depending upon that p-value, you will identify whether the data is stationary or non-stationary. So let me say here, augmented Dickey-Fuller test. This basically helps us to identify that whether our data is stationary or non-stationary. Fine. So for that, first we require to import a library here. So let's import that. Here I will say from statsmodel.tsa.statstool, stat tools, and from this I will import ADF Fuller, that is augmented Dickey-Fuller. Let's run that. So let's write a function for that. In that function, we will pass our data, and it will return us the output. So let's say a def ADF test, and here we will pass an argument which will be our data, that is our IGP column from the data frame. In this, in the result variable, we will say ADF Fuller. This is an inbuilt module that we imported right now, and in this ADF Fuller, we will again pass that data. Then we will print the ADF statistic. So let me say here ADF statistic, and here I will print the data from the 0th index of the result variable. So let me say result 0. So from this result, in this result variable, basically we are loading the ADF Fuller module that we imported from the stat model. Then in that ADF Fuller, we are passing the data, which will be an IGP column from our data frame, and then we are printing just the value on the 0th index of the result. Fine. After that, we will print the p-value here. So let me say here p-value, and depending upon this p-value, you will identify whether the data is stationary or not, and this p-value will be present on the first index of the result variable. Let me say result 1. Fine. After this, we will write an if-else block here. So let me say if result at, just a minute, result at 1. Now result at 1 basically means the p-value. So if your p-value is lower than or equal to 0.05, then it will basically enter this particular if block. So here we will print that reject the null hypothesis, because the null hypothesis basically says that the data is not stationary, and if your p-value is lower than 0.05, there your data is stationary, and hence you are rejecting the null hypothesis. Let me say reject the null hypothesis, which means the data is stationary. So this was the if block. Let's try the else one. So in this else, it will only enter if the result at 1, that is the p-value, if it is greater than 0.05, then you have to accept the null hypothesis. So let me say here, accept the null hypothesis, which means the data is not stationary. So what we are basically doing here, we are calculating the p-value not manually but with the help of ADF Fuller, that is the augmented Dickey-Fuller test. And once we calculate that p-value, then we are creating the if-else block here. So if that p-value, that is the result at the index 1, if it is lower than 0.05, then we are rejecting the null hypothesis, which says that data is not stationary. And as we are rejecting the null hypothesis, the conclusion is the data is stationary. And if the p-value, that is the result at the index 1, if it is greater than 0.05, then we are accepting the null hypothesis, which concludes that the data is not stationary. Fine. So this was the function. Now in this function, I will pass the argument here in this particular cell itself. So let me say ADF test. This is our function name. Here we have to pass the data. Data is nothing but the IGP column from the data frame DF. Now as you can see, we have no other column in our data frame DF except for this IGP, because date is now our index, so that's not a column anymore. Apart from IGP, we don't have any column here. So for that, what I will say, I won't specify the IGP column from data frame. I will just say data frame dot values, because we don't have any other column apart from that. So let's run that. So as you can see, it's saying that the p-value is 0.849, which is quite high as compared to 0.05, and hence we are accepting the null hypothesis, which says that the data is not stationary. And that's what we even concluded after looking at this particular graph. Even from here we saw that the data was not stationary, but we still opted for a practical mathematical method, which was ADF test, and it again says us that the data is not stationary. So the Arima model cannot handle this non-stationary data. Hence, it's mandatory to convert it into stationary. Now to convert the data into stationary, let me write here, converting the data into stationary. So to convert the data into stationary, we can either go ahead with the differencing method or the log transformation method. Here in this particular project, we will go ahead with the differencing method. Now there are multiple differencing you can do. You can start with first order differencing, then second order differencing, and then you will go ahead. So first you will perform differencing, then you will check whether that differencing is making the data stationary or not. If it is still not making the data stationary, then you will go ahead with the next order differencing. So we will always start with the first order differencing here. So we will say DF. In this DF data frame, we will add a new column of first order. Here we will say DF, and the differencing that we want to perform is on the IPG column, this particular one. Then here you will say difference. Fine. So you won't put anything here in this differencing parenthesis, because you are performing first order differencing. Even if you put 1 or if you remove that 1, it won't make any difference. Fine. If you are performing the 12th order differencing or the 7th order differencing, then you can put the values here like 12 or 7. But right now you are just performing a single order differencing. Hence you won't put anything here. Fine. Let's run that. Let's display the data frame again. So as you can see, now we have one more column here, which is first order, and the first value is nan, that is not a number. This is because for this first value 3.33, we don't have any preceding value to subtract from, and hence we have not a number here. But for this particular value, which is 0.0255, we have this value, current value, and the preceding value, which is 3.33. So when you subtract this from this, you will get this answer, which is 0.255. Fine. Now it's also mandatory for us to drop this null value here, because if you check here, if you say df.isNA.sum, you can see now you will have a one null value in the first order column, as you can see here. So it's mandatory to drop it. And so here I will say df dot drop na and in place is equal to true in order to make the changes permanent. Let me run that. Okay, there's a mistake actually. We don't require this dot. Fine. So after dropping this null value, if you check it again, let me say df dot head here. Now you won't have that null value anymore. As you can see, now that first row has been deleted, we just have from the second row itself. After doing that, now we will pass this first order column to our ADF test to check whether this data is now stationary or not. So here I will again call that function, which is ADF test. And from this, now I will pass the first order column. Now I have to specify the column name, and I can't just say df.values because we have more than one column. So here I will pass the first order. Let me run that. So now if you take the look at p-value right now, you can see, don't look at this 2.85. It's actually e raised to negative 18 after that. Fine. So it's a very small value which is lower than 0.05, and hence it's saying that now reject the null hypothesis and the data is stationary. Fine. So now the data has been converted into the stationary format, which means now we can use this data for further feeding to Arima model. You can even check that by plotting. Let me say here df, the column name which is first order, and here I will say plot. Let me also give the figure size, which is 18,5. Let's run that. So now you can see you are having the data with a constant variance, and you can see now it's oscillating around the mean of 0. It is not showing any kind of uptrend or downtrend, but it is just constant on one single line. Fine. You can see there's a lot of difference between this particular graph and the previous graph which we had. So now this data is stationary, and the stationary data will always look like this, like it's oscillating around the mean of 0 with a constant variance. Fine. So this was the third stage of our project, which was checking whether the data is stationary or not. If it is not stationary, then making it stationary explicitly. Now we will perform the fourth stage here. So let me say fourth, which is train test split. Now you can split your data into the training set and the testing set in any ratio. It can be 70-30, it can be 80-20 and anything. Here I will be going ahead with the 80-20 ratio. That means the 80% of the data will be in the training set and 20% of the data will be in the testing set. So here we cannot make use of the train test split module from scikit-learn. We have to do this manually. So let's check what is the 80% of the total data frame first. So what's the total length of our data frame? Let's check that. It was around 1026, and then we deleted one row. Now it's 1025. So let's calculate what is 80% of this. So let me say here 0.8 into length of data frame. So 80% of the entire data frame is 820, which means out of 1025 rows, 820 rows will be in the training set and the remaining rows will be in the testing set. So let's create that manually. Let me say here train. Now in this data frame, we just have to pass the first order column and not the IPG, because that's our data before making it stationary. After making the data stationary, we have stored it in the first order column. Hence we'll just pass that. And in order to pass it in the data frame format, we have to add one more square bracket here. So we basically require two square brackets, because if we just put a single square bracket here, then that will make the data convert into an array format and not into data frame. Fine. After that, we have to put first 820 rows in the training set. So we will make use of slicing here, list slicing, and 820. So starting from the 0, that whatever the first index is, up till 820, the rows will be stored in the training set. Only the rows from the first order. Fine. And in the testing set, we will say df. Again, the column name would remain same. So first order. And the remaining rows. That is, the starting index now will be 820, and up till the last index, whatever it is, like 1025 or 1024, up till that it will be in the testing set. So this was the train test split. Let me run that, and we can even check the shape of that. So let me say train.shape and test.shape. As the training and testing right now is in the data frame format, you can make use of shape method to check its dimension. Fine. So as you can see, for the first 820 rows are in the training set and 205 rows, the remaining 205 rows are in the testing set. So this was the train test split. Now we are heading to the fifth stage, which is determining the Arima parameters, which are P, D, and Q. So these are the three parameters of Arima model. P is associated with AR model, that is auto-regressive. D is associated with how many differencing that we have performed in our model, and Q is associated with the moving average model. Fine. So there are two ways for determining these parameters. Either you can determine it manually by plotting the ACF plots, that is autocorrelation plots, and PACF plot, that is partial autocorrelation plot. But when you manually determine these PDQ parameters, you always end up making below average predictions, because no matter how hard you try to interpret them, it never gives you that much efficient results. Fine. So hence we will be going ahead with the second method, which is of Auto-Arima, and this Auto-Arima is an inbuilt method which directly gives us what will be the best parameter for our model depending upon the data that we are feeding it. And hence we will go ahead with the Auto-Arima module. This Auto-Arima module basically takes our training data and it determines the factors, that is, it determines this particular parameters, what P, D, Q values will be beneficial for our model, and then it returns that parameters to us as output. So this is the automatic way of finding the P, D, Q parameters, and we will go ahead with that. So for this Auto-Arima, we require that module first. So let me go back to the first cell, and here first we have to import PMD Arima. So here let me say pip install PMD Arima. Let's run that. Because your Auto-Arima module is present in this particular library of PMD Arima. After running that, let me hide this output. Here I will import that Auto-Arima module. So let me say from PMD Arima, we will import Auto-Arima. Let's run that. So let's go back to the Auto-Arima part. Here we will create a variable. Let's name it as Auto-Arima. And in this, we will load our Auto-Arima module that we imported right now. So let me say Auto-Arima. In this, we have to pass our training data. Let me say train, and then we have to provide one more parameter here of seasonal. So if your data is seasonal, you have to say true, and if your data is not seasonal, that is in this particular case our data is not seasonal, so hence we will say false. And also the Arima model cannot handle seasonal data. If you want to work with seasonal data, then you have to use the extension of Arima model, which is seasonal Arima, S-Arima. Fine. As this is Arima model, it cannot handle seasonal data, so the seasonality is false. Let's run that, and let me print the Auto-Arima summary. So this will give us the summary of our Auto-Arima. Let's run that. So as you can see, it has given us what the PDQ values will be beneficial for our particular data. So as you can see here, it has given 202, the P value as 2, D value as 0, and Q value as 2. So these are the values that we will be using for our parameters PDQ. Even if you want to check it, you can say something like this here, Auto-Arima dot order. Let's run that. So as you can see, this is the order that the Auto-Arima have chosen for our particular data. Fine. So now we will start building the Arima model. So let's write, this is our sixth stage of the project now, which is building the Arima model. Let's run that. And for that, we first have to import the Arima module from the stats model. So let me go back to the first cell. And here I will say from stats model dot tsa dot arima dot model. Here we will import the Arima. Let's run that. And let's go back to the Arima stage, building Arima actually. Here we'll create the model. Let me say model is equal to, we will import the Arima module, and then we will pass our training data here, which is train. And then we also have to specify the order. Order is nothing but the PDQ parameters. So you will specify whatever the parameters Auto-Arima have chosen for you. So just copy this Auto-Arima.order and paste it here. Let's run that. So this was about building the Arima model, and now the Arima model has been built. Next thing that you have to do is you have to forecast now. Fine, let me hide this and let me write here the 7th stage, which is forecasting the data. So you will create the forecast variable here. Let me say forecast is equal to, then the Auto-Arima, this is the variable in which you have loaded your Auto-Arima module, dot predict. Now for what you have to predict, you have to give the periods here. That is for how many time period you want to predict the data or you want to forecast the data. So let me say n periods, and in this I will give the length of testing set. So whatever will be the length of testing set, for that many number of periods it will predict the data. Fine. Then you will create a new column in your data frame named as forecast. Now in this forecast column, what you have to do, you have to add this forecasted or predicted values, but you also have to keep this thing in mind that the forecasted values are only for the remaining 205 rows, that is for the testing set, length of testing set. For the first 820 rows, that is in the training set, you want to add the none. So let me say here none. This will be added in the first 820 rows. So let me say length of train. That you will add the forecasted values here. So forecast. Let's run that. After that, let's display the data frame here. Let me say df head. So as you can see, now we have this forecast column, and you can see it consists of nan values, but it will consist the nan values only for the first 820 rows, which was our training set. But it has predicted the values for the remaining 205 rows, which were in the testing set. Fine. So let's plot that. So in this plotting, we are going to plot two things. First thing is the first order column, that are our original values, and the second thing is the forecast. So let me copy it from here and paste it here, and then let me also give the figure size here. So plot fig size, which is, let's give as 20,5, and let's run that. So as you can see, it has given this orange line, which is the forecasted data only for the year up from 2008 till 2024, because only that part of the time was in our testing set, and for the training set we haven't predicted anything. Fine. So right now it's very overlapped onto each other because it consists of a lot of data. Let's try plotting only the forecasted values on the top of only the test set. So for that we require matplotlib. Let me import that first. Let me say import matplotlib.pyplot as plt. Let's run that. So let's go back to that and let's try to print only the forecasted portion, that is from 2008 up till 2024. Fine. So let me give the figure size first. So plt.figure, then the fig size, and let the figure size be 15,5. After that, first you will say plt.plot. It will give you the line plot, and in this you will pass the first the original data, which is the first order. So df first order, this is your original data, but not the entire data, that is not the training data, only the testing data. Hence you will also add the list slicing here, that is after 820, that is the remaining 205 rows of the testing set. Then let's give the color of line as blue so that we can distinguish between them, and we can also add the label here, which is actual values. So this was the first line plot. We will try to plot one more plot here. Let me copy it and paste it here. Now this particular second plot won't have the first order column but the forecast column. Let me say here forecast, and again this particular thing will remain same, that is we want the remaining 205 forecasted values, and let's make the color as red and the label as forecasted values or the forecast values. Fine. So these are the two line plots. Now we will also give the title to our chart. So let me say plt.title. In this title we will say Arima model results. Then on the X label we will add the date, just a minute, and on Y label we will add IGP, industrial gas production, and then we also want the legends to be added, that is the titles of the line plots. So let me say legend, and let's run that. So as you can see, the blue line signifies our actual values and the red line signifies our forecasted values. And as you can see, the forecasted values are exactly on the top of actual values. There is a slight difference. I know that somewhere the actual values are extreme, but the forecasted values are not that extreme. Hence, they haven't reached very peak. But still, the forecasted values are overlapping on top of actual values, which means the prediction is good. Fine, it is capturing all trends here and it's performing really very well. So this was the final results of our Arima model, where we can easily conclude that the forecasted values are exactly matching the actual values. There is just a slight difference, but apart from that slight difference, everything is equal to each other. Fine. So this was one parameter of checking whether the forecasted values are close to your actual values or not, and we can conclude that everything from this particular chart. But there is also another way of computing the mean absolute error and the root mean squared error. So let me say here, evaluation metrics. Fine, and let me import that first. So here I will say from sklearn.metrics, I will import the mean absolute error and mean squared error. This one. Let's run that. And we also require numpy here actually. Let me also import that. Import numpy as np. So going back to that, let me compute the mean absolute error first. So mean absolute error is equal to, we will load that module, mean absolute error. In this mean absolute error, we will pass our original data, which that is present in the first order column, and the forecasted data that is present in the forecast column. So let me say here df first order and only the testing set, that is from 820 up till the end, and then the forecasted values which are present in the forecast column, again from 820 up till the end. Fine, and let me print the mean absolute error here. So let me say mean absolute error, and here I will pass that MAE. Let's print that. So as you can see, this is your mean absolute error, which is quite low. After that, we can also print the root mean squared error. Now we don't have any direct function for that root mean squared error. Root mean squared error basically is the square root of the mean squared error, and we have imported the mean squared error. So we will just take the square root of that using numpy. So let me say here root mean squared error and MSE. Then I will say MP. Then I will say NP, that is numpy dot square root. And here I will take the square root of mean squared error. And in this mean squared error, I will again pass this first order column and the forecast column. So let me copy it from here itself. And then here I will say again, I will print that actually. So print root mean squared error. And here I will pass that RMSE. Let's print that. So as you can see, the root mean squared error is 4.4. So this was the two evaluation metric which you can also plot for your Arima model. And this was the entire project, where we tried to divide our project into various stages. We pre-processed the data, we tried to make it stationary, we performed train test split, we analyzed the best values of our parameters, that is PDQ. We built the Arima model using that parameters. And then we tried to forecast the data. Here it was overlapping, and hence we tried to build a different plot for that. And from this plot we concluded that the forecasted values are very close to the actual values, which means the forecasted data is efficient and the model is performing really very well. And then we also tried to print the evaluation metric. So that's it for the video. Thanks for watching.